Bismillahirrahmanirrahim. Assalamu alaikum students. In this lecture we are going to learn proof techniques and strategies, and it covers section 1.7 and 1.8 of your textbook. So let's have a look at the outline of the lecture. We'll start with the terminology used in the lecture throughout, and then we'll try to find out the answer of the question, what is a proof, and then there are few methods of proving theorems, and then we learn common mistakes which we make in proofs, and then we learn few proof strategies, how to find a proof, and then finally we'll solve few exercise questions, and for this we will have to watch next video. So for your information, this lecture consists of two parts. First part, this is the first part of the lecture, and in next part 2 of the lecture, you can see a few questions from exercise I'll be sharing with you. So first of all, proof terminologies. Theorem. Theorem is a statement that can be shown to be true. Proof. Proof is a valid argument that establishes the truth of the theorem. Axioms are the statements we assume to be true. Lemma is a less important theorem that is helpful in the proof of other results. Corollary is also a theorem that can be established directly from a theorem that has been proved. Conjecture is the statement that is being proposed to be a true statement. So, keeping all the terminology in mind, now we know that a proof is a valid argument that establishes the truth of the theorem as a conclusion. Now, statements in a proof can include the axioms, the premises, and the previously proved theorems. Now, in order to put all this information together, we use rules of inference and to achieve the final conclusion of the theorem. Learning objectives of the lectures are learning a few methods of proofs, and which consists of direct proofs, proof by contrapositive, proof by contradiction, and proof by cases. So let's begin with first method, direct proofs. Direct proof follows the following steps. First step is premise, and then subsequent steps use rules of inference or other premises, and finally last step proves the conclusion. In simpler words, a direct proof of a conditional statement P implies Q first assumes that P is true and then uses axioms, definitions, previously proved theorems with rules of inference to show that Q is also true. Now the above targets to show that the case where P is true and Q is false never happens. Thus, P implies Q is always true. So let's have a deeper understanding of the method by solving this question. Show that if n is an odd integer, then n square is odd. In order to prove using direct proof method, we'll assume that n is an odd integer. Now since n is an odd integer, then n can be written as 2k plus 1, where k is any integer. Now squaring both the sides, we have n squared is equal to 2k plus 1 square, which is equal to 4k square plus 4k plus 1. And by taking common, 2 common from first two terms, we have 2 into 2k square plus 2k plus 1. And this is an odd number. So this implies n square is odd. So let's have a look at another example. Question here is, show that if m and n are both square numbers, then prove that mn is also a square number. Now in order to prove this by direct method, we'll assume that m and n are both squares. This implies that there are integers u and v such that m is equal to u square and n is equal to v square. Then mn is equal to u square into v square, which is equal to uv whole square. And this implies mn is a square, and hence the result. There is another exercise. Prove that if n is an even integer, then n square is even. So let's start the proof by assuming that n is even. Then n can be written as n is equal to 2k for some integer k. Squaring both the sides, we have n square is equal to 2k square, which is equal to 4k square, and which can be written as 2 into 2k square. And it means this is even. This implies n square is even, and hence the result. So this is the formal version of the proof with the reasons. Okay, next method, technique 2, proof by contrapositive. So this is an indirect proof method starting with the contrapositive equivalence. We know that P implies Q is equivalent to negation Q implies negation P. So if we are asked to prove that P implies Q, we instead prove negation Q implies negation Q. Negation Q implies negation P. So why do we need this method when we know direct method? So sometimes it may be easier to directly prove negation Q implies negation P than P implies Q. So simple steps to implement the method. The proof by contrapositive method makes use of the equivalence P implies Q is equivalent to negation Q implies negation P. Now to show that the conditional statement P implies Q is true, we first assume negation Q is true and then use axioms, definitions, prove theorems with rules of inference to show that negation P is also true. So proof by contraposition, example number 1. Show that if 3n plus 2 is an odd integer, then n is odd. Now since we have to prove this by contraposition, so we will assume the negation of q, that is negation of n is odd. So negation of n is odd is n is even. So let's assume that n is even. This implies that n can be written in this form, n is equal to 2k for some integer k. Then 3n plus 2 is equal to 3 into 2k plus 2. We just plugged in the value of n, which is 2k, and this is equal to 6k plus 2, and which is equal to 2 into 3k plus 1, and 2 into 3k plus 1, that is some integer multiplied by 2, which is even number. Since the negation of conclusion implies the negation of hypothesis, so the original conditional statement is true. Another example of proof by contraposition. Show that if n is equal to ab, where a and b are positive, then a is less or equal to square root of n, or b is less or equal to square root of n. Again, we are going to prove this by contraposition. So we have to prove the negation of, we have to assume the negation of conclusion. And conclusion in this case is a is less or equal to n, or b is less or equal to n. So its negation will be a is greater than square root of n and b is greater than square root of n. So let's assume both a and b are larger than square root of n. So this implies their product is greater than n, so that n is not equal to ab. Since the negation of conclusion implies the negation of hypothesis, the original conditional statement is true. Proof by contrapositive, another question which we have already done with direct proof method. So let's see how can we do same question with another method. And the question here is, if n square is an even integer, then n is even. That is, we have to prove that n square even implies n is even. So by the contrapositive, this is same as showing that negation of n even implies negation of n square even. So if we negate the statement n is even, so we have the statement n is odd. So let's assume n is odd. Then n square is odd. We already proved this on slide number 8. Since we have proved the contrapositive, negation n even implies negation n square odd. So we have also proved the original hypothesis. That is all for this proof. Next technique, technique number 3, proof by contradiction. Again, we have to prove the conditional statement P implies Q, that is if P then Q. And our proof strategy in this case is assume that negation of Q. We have to prove Q whenever prove Q is true whenever P is true, but we assume that P is true and Q is false. That is, negation of Q is true. In other words, assume that P and negation Q is true. Then arrive at a contradiction P and negation P, or something that contradicts a known fact. Since this cannot happen, our assumption must be wrong, and in conclusion, we'll say that negation Q is false and Q is true. So, in order to have deep understanding of the method, let's consider an example. Show that if 3n plus 2 is an odd integer, then n is odd. So let's assume the contradiction, that is the negation of Q. Let's assume that this statement is false, that is, conclusion is false, n is odd, is false. So if n is odd is false, then n is even, and we have 3n plus 2 is odd and n is even. Now the later implies that n is equal to 2k, that is, if n is even, then n can be written as n is equal to 2k for some integer k. So that 3n plus 2 is equal to 3 into 2k plus 2, which is 2 into 3k plus 1, and which implies 3n plus 2 is also even, which is contradiction to the fact that 3n plus 2 is an odd integer. And so our assumption was wrong. Our assumption, which was n is even, was wrong. So the original statement is true. Next example, show that square root of 2 is irrational. Now we'll suppose otherwise, that is, square root of 2 is rational, and then we'll end up with a contradiction to prove this statement true. Assume on the contrary that it is rational. Then it can be expressed as a over b for some positive integers a and b if b is not equal to 0. And further we restrict a and b are in their lowest form. That is, there is nothing common between a and b except 1. So keeping all these facts in mind, let's proceed that square root of 2 is equal to a over b. This implies by squaring both the sides, a square is equal to 2b square. Now a square is equal to 2b square means where a and b both are integers, means a square is even. If a square is even, we have already seen that if a square is even, a is also even. This implies a is even. So if a is even, then a can be written as 2c for some integer c. Now by plugging in the value of a into this equation, we have 2c square is equal to 2b square, and this implies by simplification b square is equal to 2c square. Now b and c both are integers, then this implies b square is an even number, and this implies b is even. So but we assume that a, b are in its lowest position, lowest form, but we ended up with a contradiction to this fact. So our original statement is true and our assumption was wrong. Next type of proof is Nyquist proof. We can quickly prove that a conditional statement P implies Q is true when we know that P is false. If P is false, then P implies Q is true. Because P implies Q must be true when P is false. We have already discussed this fact in the class while defining the conditional statements. So consequently, if we can show that P is false, then we have a proof called a vacuous proof of the conditional statement P implies Q. Let's have an example of vacuous proof. Show that the proposition P0 is true, where Pn is, if n is greater than 1, then n squared is greater than n. And the domain consists of all the integers. Now let's proceed with solution. Note that P0 is, if 0 is greater than 1, that is, replace n by 0 in Pn. If 0 is greater than 1, then 0 square is greater than 0. Now, since P is false in this case, since hypothesis is false in this case, so by vacuous proof, we can say that P0 is automatically true. There is something which is important, and you should note that The fact that the conclusion of this conditional statement 0 squared is greater than 0 is false is irrelevant to the truth value of the conditional statement, because a conditional statement with a false hypothesis is guaranteed to be true. So next type of proofs is trivial proofs. So we can also quickly prove a conditional statement P implies Q if we know that the conclusion Q is true. By showing that Q is true, it follows that P implies Q must also be true. So a proof of P implies Q that uses the fact that Q is true is called trivial proof. So let's have an example of trivial proof. Let Pn be the statement: if A and B are positive integers with A greater or equal to B, then An is greater or equal to Bn, where the domain consists of all the non-negative integers, so that P0 is true. So the proposition P of 0 is: if A is greater or equal to B, then A to the power 0 is greater or equal to B to the power 0. Now, because conclusion A to the power 0 is true, A to the power 0 is equal to B to the power 0 is equal to 1. So, the conclusion of the conditional statement, if A is greater or equal to B, then A to the power 0 greater or equal to B to the power 0 is true. Hence, this conditional statement, which is P0, is true. This is an example of trivial proof. Note that hypothesis, which is the statement A greater or equal to B, was not needed in this, but it doesn't matter whatever the hypothesis is. Now, here is an exercise for you. You should try it yourself. Prove that if n is an integer and n squared is odd, then n is odd. And you should try this question by both direct and contrapositive techniques and see which works better. Technique 4. Proof by cases. In such problems, we are given a problem of the form P1 or P2 or Pn. There are different cases. P1 is case 1, P2 is case 1, Pn is case 1, case n, and all these implies Q. So where P1, P2 are the cases, up till n are the cases. This is equivalent to the following statement: P1 implies Q and P2 implies Q and up till Pn implies Q. So prove all the clauses are true in order to prove this statement to be true. So let's have a look at the method. This is the equivalence relation we'll follow to prove such questions. So let's have an example of proof by cases. Question here is: show that if an integer n is not divisible by 3, then n square is equal to 3k plus 1 for some integer k. Now, if n is an integer which is not divisible by 3, then n can have two forms. Either n can be written as 3n plus 1 or n can be written as 3n plus 2. There is no third form for an integer which is not divisible by 3, where m is an integer. So we'll discuss both the cases in order to prove this statement. So for the first case, when n is equal to 3m plus 1, n square is equal to 3m plus 1 whole square, and this is equal to 9m square plus 6m plus 1, and after a few simplification steps we have n square is equal to 3k plus 1, where k is equal to 3m square plus 2m, which is an integer. And this is what was required. So we have conclusion for the case 1, and if for the second case n square is equal to 3m plus 2 whole square, and this again can be written as 3k plus 1 after some simplification steps, and the k is an integer. So we obtain the desired conclusion in both the cases, so the original statement is true. So we have to prove the statement for every case. Next method is proving biconditional statements. So we may use the equivalence P if and only if is equivalent to P implies Q and Q implies P. But in general, for more cases, more than two cases, we can use this equivalence relation. There is an example. prove that the theorem, if n is an integer, then n is odd if and only if n square is odd. So what we need to do, if our P statement is n is odd and Q statement is n square is odd, then we have to prove that P if and only if Q. For this, we have to prove P implies Q and Q implies P both are true. Now, you can solve this yourself. This is for your exercise. Proof of equivalence. Show that the following statements about the integer n are equivalent. Now, the statements are equivalent if the statements P, Q, R are equivalent if P implies Q, Q implies R, and R implies P are true. So, in order to prove all these statements equivalent, we have to prove P implies Q, Q implies R, R implies P, all are true. And you will do it yourself. This is quite easy. Next method of proving is called existence proof. A proof of the proposition of the form there exists x px is called an existence proof. Sometimes we can find an element S called witness such that ps is true. This type of existence proof is called constructive. Sometimes we may have non-constructive existence proof where we do not find the witness. So there is an example of existence proof. Show that there is a positive integer that can be written as the sum of cubes of positive integers in two different ways. So show that there is a positive integer, that is there exists some positive integer. So we just need to give an example, and there is an example 1729 which can be written as 1 cube plus 12 cube, and it can also be written as 9 cube plus 10 cube. So the statement is true because we are able to find an integer which is the sum of cubes of positive integers in two different ways. Next example is show that there are irrational numbers r and s such that r to the power s is rational. So there is another example for this. This is also true. Now, common mistakes we usually make in our proofs, and we should avoid these proofs, and we should try proving with logical reasoning. There is an example of a proof which has mistakes, but apparently seems fine. Question here is show that 1 is equal to 2. So its proof is given by let a be the positive integer and b is also positive integer such that b is equal to a. Now a is equal to b implies a square is equal to ab. What we have done, we just multiplied equation 1 by b, equation 1 by a. Next we subtracted b square from both sides of equation 2, and then we factorized both sides of equation 3, and then we divided by a minus b, and we have a plus b is equal to b. And since a is equal to b, so by plugging in a is equal to b, we have 2b is equal to b, and this implies 2 is equal to 1. Now, what is wrong with this proof? In step 4, actually we divided by a minus b. We cannot divide by 0 because a is equal to b gives us a minus b is equal to 0. So this is the logical problem with this proof, so this proof is wrong. Another example of wrong proof, show that if n square is an even integer, then n is even. And now proof here is suppose that n square is even, then n square is equal to 2k for some integer k, and let n is equal to 2m. Now we have to prove that n is even. Now we are assuming that n is equal to 2m. So what we need to prove, we cannot assume. So that is why this proof is also wrong. Proof strategies. So whenever we have a statement in front of us which we need to prove, we just recall the methods and theorems we have already done so that we can have some guidance from already proven results. So first step is adapting existence proof. Example for this is that show that square root of 3 is irrational. We just have proved that square root of 2 is irrational. The strategy used in that proof can be adapted in this proof as well. Instead of searching for a proof from nowhere, we may recall some similar theorem and see if we can slightly modify its proof to obtain what we want. And sometimes it may be difficult to prove statement Q directly. So instead we find a statement P with property that P implies Q and then prove P. Now if this can be done by modus ponens, Q is true. So this strategy is called backward reasoning. So let's have an example of backward reasoning. Show that distinct positive real numbers x and y, x plus y over 2 is greater than square root of y. Now what we need to do, assuming that this is true, and we did some steps to see if it end up with a known fact. So x plus y over 2 is greater than the square root of xy. But what we did, we squared both the sides. We have x plus y whole square over 4 is greater than y, then multiplied by 4. X plus y whole square is greater than 4xy. And then expanding the square, we have x square plus 2xy, y square is greater than 4xy. And this gives us x minus y whole square is greater than 0. Now, since all these inequalities are equivalent and we started with this inequality, we ended up with an inequality which is true for every value of x and y. So this implies, by backward reasoning, this implies this the given statement is true. And that is the end of the lecture. Thank you so much.